In this class, let us take a problem of partial UDL acting on a beam where we need to find the slope and deflection. So the question is like this: a beam carrying partial UDL. It's an examination problem. Determine the slope at A and B, deflection at D and C. Take E value as 4 into 10 power 5 Newton per meter square and moment of inertia I as 5 into 10 power 8 millimeter power 4. So this is the beam. So if you observe the beam, this is a overhanging beam. So BC is the overhang, A and B are the input supports. It carries a partial UDL of 4 kN per meter from D to B over a span of 3 meters and a concentrated load of 12 kN acting at the free end C. So span is total 9 meters. The question here is we have to find out the slope at A and B. That means we need to find theta A. Slope at A is theta A. Slope at B is theta B. Then deflection at D and C. So deflection at D I will take as YD. Deflection at C as YC. So according to our sign convention, for the slopes, clockwise is negative, anti-clockwise is positive. For deflection, downward is negative, upward is positive. So depending on the value what we are going to get, we have to decide the nature of the deflection and the slope. Now the solution works like this. First we need to find the reaction. Since it is a centrally supported beam with the overhang, we need to find the reactions at the supports because we need to find the bending moment at the at one of the sections in the beam. For finding the bending moment expression, always we need to compute the reactions. So these two reactions, RA and RB, they are found out using the equilibrium equations. The first equation I am going to use sigma MA is equal to 0. So when we are using that equation, I will take clockwise moments positive, anti-clockwise moments negative. Now I am here, so I have to write the moments due to this UDL, this concentrated load and this reaction about the point A. So distances should be measured from point A. So first thing I have to take the UDL. So this UDL is converted to a concentrated load when you are calculating the moment. So concentrated load will be 4 into 3. So that intensity multiplied by the distance gives the concentrated load. So 4 into 3, 12. So it is given the clockwise moment at point A. So it is 12 into distance from point A to this UDL, midpoint of UDL is 3 plus 1.5, that is 4.5. So this is the moment due to this UDL. Then moment due to this RB reaction is anti-clockwise. So minus RB into distance from A to B is 6 meters. Then moment due to this 12 kN is positive. So plus it's clockwise. 12 into distance from A to C is 9 meters. So this should be equal to 0. So from this we can calculate the reaction RB. So if you simplify that, you are going to get the reaction as 12 into 4.5. 12 into 4.5 plus 12 into 9, that is 108, okay, is equal to divided by 6. So this is the reaction 27 kilonewton. So 27 kilonewton is positive, that means assumed direction of reaction is correct, it is upwards. Now the other reaction is found out by taking the vertical force equation sigma Fy 0, that means total downward force is equal to total upward force. So sum of the forces acting on the beam in the downward direction should be equal to sum of the reactions in the upward direction. So according to that you will be getting RA plus RB should be equal to the second equilibrium equation. Total load is 4 into 3, that is 12 plus 12. So 12 plus 12, 24. So 24 kN is the total load. Now here RB is known, therefore RA is equal to 24 minus RB. You can see here 24 minus RB, that is 24 minus 27. You are getting minus 3 kN. Please note that in this problem you are getting RA as negative. Negative means the assumed direction is wrong, so it is downward. So initially we assume If you get negative value for the reaction, then it will be in the opposite direction. Now that means this RA you are getting minus 3, whereas RB you are getting plus 27. That means this direction, instead of upwards, it becomes downwards. Now let me write once again the sketch now, because the reaction is downwards now. So I will show like this. So this is C, this is A. So at A we have negative downward reaction, which is 3 kilonewton, and you have UDL here. From here to here you have UDL. From B to B you have UDL. And at B you have an upward reaction of 27 kilonewton, and this UDL is of course 4 kilonewton per meter, and this is 12 kilonewton. The distances will change 3 meters each. Now this becomes the free body diagram of the beam now. Now the next step is very important. Whenever they give partial UDL in mechanics method, of course we are using mechanics method here also. Whenever they give partial UDL, one important thing we have to do here is, so I will write here, let us find the proper deflection by mechanics method. So according to mechanics method, we have to consider a section XX in the farthest region from the left support. So here it is a simply supported beam. I will consider X from the left end. So X is better from here. So there are 3 portions here, AD, DB and BC. So I will consider a section XX in the portion BC at a distance X from the left hand, that is from the end A. So this is what? So this is X. Now we have to write the bending moment expression at X, and that it has to be equal to EA into D square over A square by deflection equation. Now before that, one important thing here is, whenever partial UDL is given, you should keep it in mind. Whenever partial UDL is given, you have to extend this UDL up to the section under consideration. That means we have to extend this 4 kilonewton per meter from B to this XX. So since you are extending from here to here, I have to cancel the effect of that force. So what I have to do here is, I have to introduce an upward UDL also from B to XX. So both those will have the same intensity. This is 4 kilonewton per meter. This is very, very important. So what I will write here, then partial UDL is given, extend the UDL up to the section XX. Section XX, of course, it is considered in the farthest region, and introduce an upward UDL of same intensity from the end of partial UDL to the section XX. So this is very important step. Whenever a partial UDL is given, this step we have to do. So this is how we have to do. Now on the beam you have 2 UDLs. One UDL runs from D to this XX of intensity 4 kilonewton per meter. That is over a distance of, you can say, X minus 3 meters. So this UDL runs over a distance of X minus 3. Another UDL, upward UDL, because we have to nullify the effect of this UDL, I have to use upward UDL of same intensity for same length. So this upward UDL will act over a distance of X minus 6. So this distance is X minus 6. Please note that. So that is X minus 3. This is X minus 6. Okay. Now, once you introduce these UDLs, now we have to write the bending moment expression at XX. So bending moment at XX. Now I am using the Mechanics method equation. So mx, see to the left side of the section. So I have told you that irrespective of left side or right side of the section, if the force is acting downward, it is giving negative bending moment, that is hogging. If the force is acting upwards, it is giving positive bending moment, that is sagging. Now I am here, so I have applied the bending moment due to this 3 kN downward, then bending moment due to this downward UDL, bending moment due to this upward UDL, and bending moment due to this 27 kN, which is upward. So that means here, one by one I will write. I am here now, see to the left side. You have to consider all the forces, that is why you have to see to the left side and x is measured from the left hand. So first I will take this minus 3 kN. So it is negative, therefore bending moment, it is downward, therefore bending moment is negative. Minus 3 into distance is x. Okay, then bending moment due to this upward UDL. Otherwise I will write this one. So due to this reaction, I have plus, it's plus because upwards, 27 into distance from this reaction to this x-axis is x minus 6. So total is x. From that you have to deduct 6. So 27 into x minus 6 the bending moment due to this reaction 27 kN. Then downward UDL is 4 into x minus 3. So distance of the length of the UDL is x minus 3 and it acts at midpoint of x minus 3, that means x minus 3 by 2. So it is downward, therefore minus. So you should be very careful in writing the bending moment expression. If this is wrong, then other equations will be wrong. So minus 4 is the intensity into x minus 3 is the length. Midpoint will be at a distance of x minus 3 by 2. So this is the bending moment due to this downward UDL. Next I have to take the bending moment due to upward UDL. Upward UDL also will be having same intensity, but distance is x minus 6. Midpoint will be x minus 6 by 2. Since it is upward UDL, it is positive. So plus 4 into x minus 6 into x minus 6 by 2. So this is the bending moment expression. You should be very careful in writing this. Once you get this, so I will just simplify this. Mx is equal to minus 3x plus 27 into x minus 6 minus 4 divided by 2 is 2 into x minus 3 whole square plus 4 divided by 2 is 2 into x minus 6 whole square. So I will call this as equation 1. So this is the moment equation. So moment equation. So as per the Euler's Bernoulli deflection equation, this mx can be equated to ei into d square y by dx square, where y is the deflection, x is the distance measured along the axis of the beam. So here, now since mx is dispersed, this ei into d square by dx square can be equated to, it can be equated to this minus 3x plus 27 into x minus 6 minus 2 into x minus 3 whole square plus 2 into x minus 6 whole square. Okay, I think this I will call it as equation 1. Now once you integrate this, now you know how to proceed further. Once you integrate this equation, you will get dy by dx, which is the slope equation or the rotation equation. Integrate with respect to x both sides. Ei into integration of d square by dx square is dy by dx. This will be equal to minus 3 into x square by 2 or x integration x square by 2 plus 27 into, here I have already told, so in mechanics method this x minus 6 is treated as x only as a whole and it is integrated. That means it is x minus 6 whole square by 2. So this step is very important. Minus 2 into, here also we have to integrate this as x square, so it is x cube by 3. That means x minus 3 whole cube by 3. And this one also plus 2 into x minus 6 whole cube by 3 plus c1. Our strength of integration is c1. So this is the expression we get for slope. So this equation is called as the slope equation or the rotation equation because it involves dy by dx, it is nothing but theta. So this dy by dx is nothing but theta. Next, what I will do here is once again I will integrate. Integrate with respect to x once again. So I will get ei into dy by dx. Integration of d square over dx square is dy by dx. Here if you integrate, it becomes minus 3 by 2 into integration of x square is x cube by 3 plus 27 by 2 into integration of x minus 6 whole square is x minus 6 whole cube by 3 minus 2 by 3 into integration of x minus 3 whole cube is x minus 3 whole power 4 by 4, then plus 2 by 3 into integration of x minus 6 whole cube is x minus 6 whole power 4 by 4 plus c1x plus c2. So one more constant of integration gets added. So c1 plus c1x plus c2. So this is the deflection equation. Equation 3 is the deflection equation. So these things already I have explained in the earlier problems. Now we have to evaluate these two constants c1 and c2 using the boundary conditions. So we have to evaluate using boundary conditions. What are the boundary conditions that can be used here is, in the case of a simply supported beam, we know that the slope deflection is 0 at the simple supports. So that is what we have here. So here what we can do here is to evaluate the C1 and C2. Now what I will do is I will just use the boundary conditions. So the boundary conditions run like this. Let me write the boundary conditions now. So boundary conditions to evaluate the C1 and C2. Two boundary conditions we require. We know that at simple supports deflection is 0. Here A is a simple support, B is a simple support. So at A, first boundary condition is at A, the value of x is 0 at A because x is made up from A, theta is also 0. This is the first boundary condition. So since it involves theta, I have to use the second equation. So for this boundary condition, now let us substitute this. Substituting in equation 2, ei into theta. So theta is 0 here, so everything becomes 0 is equal to first term x is equal to 0 means first term becomes 0 plus second term. You see here, be careful here. Second term, if you put x is equal to 0, it becomes minus 6. 0 minus 6 is minus 6. I told in mechanics method, if any term becomes negative within brackets, that term should be neglected. That means this also becomes 0. Then this one, 0 minus 3 is minus 3, negative, neglect that term. 0 minus 6, minus 6, neglect that term. Only plus C1 will be there. So that means all these terms are zeros. Last value of C1. So according to this, the value of C1 will be 0. So this is the first value. Second value, second boundary condition is at B, that is at another simple support B, x is equal to 6. We can see here, x is equal to 6. Theta is 0. So in this case, once again, substituting in 2, in equation 2, same equation, this theta is 0, so everything becomes 0. X is equal to 6 means this term will be there. Here this term becomes 0, 6 minus 6. This term becomes 6 minus 3, 3 positive. So we have to consider that term. Here 6 minus 6 will be 0. This term we cannot take. Okay. So now here first condition x is equal to 0. You have okay, theta is equal to 0. At y is equal to 0. So at x is equal to 6 also. Oh, not theta, sorry. Theta is not 0. Y is equal to 0. Deflection is 0. This one. Okay. So deflection is 0 in the simple support, not this slope, because the deflected shape of this will be like this. something like this. Okay, this is the deflection. That means this is your theta A, this is your theta B, and this is YC, and this is Y. So these four things we need to find. So Y is 0. So that means we have to substitute in equation 3, not in equation 2. Equation 3 we have to substitute. In this equation we have to put. So this equation 3 is EI into Y. It is not given by X, it is Y. So this is the deflection equation. So there, so I have to put LHS becomes 0 now. This 0 is equal to RHS will be, so this becomes minus half into x cube. So x is 0 there, therefore the first term will vanish. Second term becomes negative, 0 minus 6 is minus 6, negative, so neglect this term. 0 minus 3 is minus 3, negative, neglect this term. 0 minus 6 minus 6, negative, neglect this term. C1x means it is also 0 because x is 0, only C2 will be there. So what we can, all the terms become 0, the last term will be C2, therefore C2 is equal to 0. So C2 is equal to 0 is the first, that is the first value of the constant of integration. Second value at B, once again at B, at the other support, x is equal to 6 meters, y is equal to 0. So there is no deflection at the simple support here. So they are the conditions. Now substitute once again this condition in 3. Substituting in 3, let us see what happens. LHS becomes 0 here, this becomes 0. Here x is equal to 6. So this you have to consider, this becomes 0. This is 3 only, we have to consider this becomes 0. This becomes 6 is C1 plus C2 like that. So okay, so for LHS is 0, first term is minus x cube by 2, that is minus 6 cube by 2. Substitute the value of x as 6. Then plus second term, this second term is, of course this becomes 9 times. So 9 by 2 into 0. So 6 minus 6 will be 0. Third term minus 2 by 3 minus 2 by 8. R can be written as 2 times. So it can be written as minus 1 by 6. So minus 1 by 6 constant into x minus 3 to the power 4 means 6 minus 3 to the power 4, which is 3 power 4. Which is 3 power 4. Then this term becomes 0 because x is equal to 6 means x minus 6 will be 0. So plus 0, that term will vanish. Plus C1 into 6, x is 6, plus C2 is 0 from this. So now, if you simplify this, you get the value of C1. So 6C1 is equal to, if you bring to this side, so 6 cube by 2. 6 cube is 216, and divided by 2 means it is 108. So 108, if you bring to this side, this becomes plus 3 power 4 divided by 6 is 81 divided by 6, which is 13.5. 13.5. Then, okay, that's all. Only these two terms. So therefore, C1 will be 13.5 plus 108 divided by 6. So it is 20.25. 20.25. So we got the two values, that is C1 and C2 we got. So C1 is C1 is equal to, we got C1 as 20.25 and C2 is 0. So these two constants of integration values we got now. Now once you get these two values, now you can substitute back those values in 2 and 3 to get the general slope and deflection equations. Now substituting for C and D, I will write here, substituting for C1 and C2 in 2 and 3. So equation 2 now becomes, so EI into theta, I can write it as theta, EI into theta is equal to minus 3 by 2 x square plus 27 by 2 x minus 6 whole square minus 2 by 3 x minus 3 whole cube plus 2 by 3 x minus 6 whole cube plus C1 is 20.25. This equation I call it as equation 4. This is this general slope equation. So by putting values of x, you can get the values of slopes at different points on the beam. Equation 3. Equation 3, if you substitute C1 and C2, minus half into x cube plus 9 by 2 plus 9 by 2 into x minus 6 whole cube minus 1 by 6 into x minus 3 whole power 4 plus this term will be 1 by 6. 1 by 6 into x minus 6 whole power 4 plus 20.25x plus C2 will be 0. So this is the fifth equation, that is the general deflection equation. Now let us see at what points he has asked the slope and deflection values. So once you get the final expressions for slope and deflection, now you can go on substituting value of x, and once again keep that in mind that after substituting value of x, if any term becomes negative within brackets, that term should be neglected, omitted, or it should be taken as 0 for computing the slope and deflection. Now let us see, he has asked for the values, determine the slopes at A and B. So one by one, there are 4 values we have to find out, theta A, theta B, yc and yd. So one by one we will calculate. So first one, I calculate slope at A, which is nothing but theta A. To find out theta A, put x is equal to 0, because at A x is equal to 0 in equation 4, because 4 is the slope equation. So what I will get here is theta into theta A, theta becomes theta A is equal to, so the first term becomes 0 because x is 0, second term also becomes 0 because 0 minus 6 is negative, I have to omit that. This also 0 minus 3 minus 3, omit this term, 0 minus 6 minus 6, omit this term, only 20.25 will be there. 20.25. So therefore theta A is equal to 20.25 divided by 9. So later on we will substitute for here and get the value in radians. So this is the first answer. Second answer, of course this is positive, therefore it is anti-clockwise. Next, slope at B, support B, which I call as theta B. So here to get theta B, put x is equal to 6, because B at B, x is equal to 6 meters. X is measured from A to B distance is 6 meters, you can see that. So in same equation 4, so EI into theta B, theta A becomes theta B now, is equal to, now put x is equal to 6 here in this equation 4, minus 3 by 2 into 6 square, minus 3 by 2 into 6 square, plus 27 by 2 into 0, it becomes 0, 6 minus 6 will be 0, then this is 6 minus 3 will be 3, so minus 2 by 3 into 3 cube, you will get, then this one 6 minus 6 becomes 0, last term 20.25 will be there. So this is the, if you simplify this, you will get theta B. So theta B is equal to, if you simplify that, let me simplify it. So theta B is equal to, so minus 2 by 3 into 36, that means minus 3 into 18, you can take, it becomes minus 54, of course this term becomes 0, here minus 2 into 9, so that is minus 18 plus 20.25. So this is the minus 51.75. Minus 51.75 divided by A. So here it is negative. Negative means it is clockwise. Slope is clockwise. Our rotation is clockwise. Then the third value I need deflection at D. Deflection at D. D is the starting point of that partial median, which I call it as YD. So since you need deflection, you have to use equation 5. So equation 5 is the deflection equation, dI into y. dI into y is equal to this much. So deflection, if you substitute input x is equal to how much? 3 meters. X is equal to, so d, the distance from A to D is 3 meters. Put x is equal to 3 in equation 5. So EI into YD. So this becomes YD, deflection at D is equal to, so put x is equal to 3 here, minus half into 3 cube plus 9 by 2 into, see here, this becomes 3 minus 6 whole cube, this becomes negative, therefore this term you have to omit. Then minus 1 by 6 into 3 minus 3, x is 3, 3 minus 3 is 0, this term becomes 0. Here also 3 minus 6, it becomes minus 3, you have to omit that, that term, so plus 0, plus 20.25 into x is 3. So you have to simplify this, you will get YD. So YD is equal to, here you can see this is 27 divided by 2, that is minus 14.5. So just I will simplify, sorry, 13.5, minus 13.5. This becomes 0, these are all zeros, plus, so if you multiply this two, you get 60.75. So you will be getting the value as 47.25. 47.25 divided by d. So you are getting positive value of deflection, that means deflection is, you are getting upwards. You can get upward deflection, there is no, always, you will not be knowing initially. So once you get the final value, then you can write the deflected curve and etc. So upward deflection. Next, lastly, I need deflection at C. So deflection at C means YC. So YC I need. So this, if you want YC, put x is equal to 9, because the distance from A to C is 9 meters. In equation 5 only, the deflection equation, EI into YC is equal to, now here you can see minus half into 9 cube, all the terms will come here, plus 9 by 2 into 9 minus 6 is 3 cube, minus 1 by 6 into 9 minus 3 is 6, so 6 power 4, plus 1 by 6 into x minus 6, that is 9 minus 6 is 3 power 4, then plus 20.25 into 9. So this is the equation. So now YC will be equal to this entire thing divided by EI. So let us simplify that. Minus 9 cube by 2. So that is minus 9 cube. I can take 9 cube divided by 2. So it is minus 364.5 plus, so be careful here. 9 into, I can write it as 4.5. 9 divided by is 4.5 into 3 cube means 27. So you should be very careful in simplification. Then minus 6 cube will be there, that is 216 you will get. Then plus, this is 81 by 6. So plus 81 divided by 6, you will get that. Then plus 20.25 into 9. So you will be getting minus 263.25. Minus 263.25 divided by 8. So deflection you are getting negative, that means this is downward deflection. So deflection at C is downward, deflection at D is upward. So once again I will check this value, 9 cube, that is minus 9 cube, okay, plus 9 into, that is 4.5 into 27, 3 cube, then minus 216 plus 81 divided by 6 plus 20.25 into 9. So minus 263.25 divided by 8. So these are the values we got. Now we have to substitute the value of EI to get the final answer. Let me substitute the value of EI. Of course, already I have told in the last problem that EI better you substitute in kilonewton meter units, and then you will get the slope in radians, and deflection of course we are going to get in meters. Then later on we can convert into millimeters. Now let me see how this can E into I can be converted to kilonewton meter. So if in any problem E and I values are not given, means the answers of theta and y will be in terms of EI only. EI will be in the denominator. That means the slope and deflection reduces with increasing the values of EI and EI. That is the meaning. That means if the beam is more stiffer, EI gives is a measure of stiffness of the beam, which is called as flexural rigidity. If the beam is more stiffer, definitely the deflection and slope will be less. So E into I, let me see what is the value of the E into I. E is given as 2 into 10 power 5 Newton per mm square into I is given as 5 into 10 power 8 millimeter per watt. So these are the units what he has given, but let us convert this into kilonewtons and meters. So it is 2 into 10 power 5. So this step is important. Newton to kilonewton is 10 power minus 3. It becomes kilonewton. Divided by millimeter to meter is 10 power minus 3 square. 1 mm is 10 power minus 3 meter square of that. So this becomes kilonewton per meter square into here 5 into 10 power 8 into 1 mm is 10 power minus 3 meter to the power 4. So meter power 4. So this is the conversion. So now let me multiply this 2 and 5 here. It becomes 10. 2 into 5 is 10. Here you can see here this is 10 power 5 into minus 5 minus 3 is 2. If this goes to numerator, it becomes plus 6. So finally it is 2 plus 6 is 8. So this becomes 10 power 8 into this 5 already I have taken here. 10 power 8 into 10 power minus 12 means 10 power minus 4. 8 minus 4 is minus 4. So this we are going to get in kilonewton meter square. So kilonewton per meter square into meter power 4 will be kilonewton meter square. So that means finally what you get here is it is nothing but 10 power 1, 10 power 8, 10 power minus 4, that is 9 minus 4, it is 5. So finally you are going to get 10 power 5 kilonewton meter square. So this is the value of EI. We have to substitute in those 4 expressions, theta A, theta B, YD and YC. Then you will get the value of slope in radians, deflection will be in meters. Later on you can convert that into millimeters. Now let me substitute the value of EI in all the 4 expressions, and let us write the answer. So slope will be now theta A. Substituting for EI in all those expressions, theta A will be now 20.25 divided by 10 power 5. Theta B will be minus 51.75 divided by 10 power 5. Then you have YD 47.25 divided by 10 power 5, and YC is minus 263.25 divided by 10 power 5. So this value, first 2 values will be in radians because they are slopes. Next 2 values will be in meters because they are deflections. So the first value, just like I write it as 2.025 into 10 power minus 4. Yes, I can write that. 20.25 to 10 power minus 5. I can write. So this is in radian. So of course very small value. This is one answer. Second answer is, so this positive means it is anti-clockwise. Then second answer, minus 5.175 into 10 power minus 4. This is also in radian. Negative value means it is clockwise. So this rotation is clockwise. Next, YD value. You will be getting in meters, which is 4.725 into 10 power minus 4 meter. Meter to millimeter to convert, you have to multiply by 10 power 3. That means it is 4.725 into 10 power minus 1 will come. That is 0.4725 mm. So this you are getting positive value means the deflection is upwards. Similarly, this value minus 2.6325 into 10 to the power of course you have to multiply by 10 power 3, you know. So it becomes 10 power, okay, one thing I do, minus 263.25 into 10 power minus 5 into 10 cube. So this will be the value in millimeters. Okay, that means it is 10 power minus 2 here. That means divided by 100 means minus 2.6325 mm downward deflection because it is negative. So these are the values we are going to get as slopes and deflections. So slope positive value shows that it is anti-clockwise gradient. Deflection positive value upward, negative value downward. So this is how we handle the problem. Why I have taken this problem is whenever partial UDL is given, you have to extend the UDL up to the section under consideration and introduce equivalent UDL in the opposite direction. Then you use the Michaelis method, write the expressions for bending moment, slope and deflection by integration. Then obtain the constants of integration C1, C2 by adopting the respective boundary conditions. The remaining procedure is same.